Electron configuration is the distribution of electrons of an atom in orbitals. Electrons naturally arrange themselves within atoms, so they occupy the positions where they have the least possible energy, because the most stable state of an atom is that in which all of the electrons have the least possible energy. Electrons in the first level, which is close to the nucleus, have less energy than those in the second level. As energy level increases, the amount of energy that the electrons in the level have increases as well. The same rule applies to sublevels. Electrons in the S sublevel have less energy than those in the P sublevel of the same energy level, and so on. The first sublevel. To represent the arrangement of electrons, we can use an orbital diagram. Each box in the diagram represents an orbital, and each group of boxes represents a sublevel. Only 2 electrons may occupy a single orbital, and these electrons must have opposite spin. The electrons will always occupy the orbitals that require the least energy. The P, D, and F sublevels all have several orbitals. For these sublevels, a single electron with the same spin will occupy each orbital within the sublevel before a second electron goes into any of the orbitals. The orbitals fill in this order because it takes slightly more energy for 2 electrons to share an orbital. Using this information, we can write electron configuration notation. Electron configuration notation is an easier way to show the arrangement of electrons compared to orbital diagrams. In this notation, superscripts show the number of electrons in each sublevel. In this example, we see helium has 2 electrons that are located in the 1s orbital. The sum of the superscripts give the total number of electrons in the atom, which equals the atomic number for a neutral atom. Although the electron configuration notation shows the number of electrons in each sublevel and is easier to express, it doesn't show how the electrons are distributed in orbitals within each sublevel, like an orbital diagram does. The order in which electrons fill sublevels can be determined by using a sublevel diagram as shown. The arrows indicate the order in which the sublevels fill. The sublevel diagram is read from top to bottom and from the arrow's tail to its tip. You may notice the 4s orbital gets filled after the 3p orbital, even before the 3d can be filled. This is because the d sublevels have higher energy than the s and p sublevels. The 4s sublevel has less energy than the 3d sublevel, so it fills first. Each different color on this periodic table represents a block. Purple is S block, yellow is D block, green is P block, and blue is F block. These blocks are named after their characteristic orbital, S, P, D, and F. Each block represents a group of elements whose highest energy electron is in the same sublevel. The highest energy level of each atom of an element corresponds to the period to which it belongs in the periodic table. However, the elements in the D block are 1 level below their period number, and the elements in the F block are 2 levels below their period number. However, there are some exceptions to the expected models. The 2 main exceptions are chromium and copper. This is because a completely full or half-full D sublevel is more stable than a partially filled D sublevel, so an electron from the 4s orbital is excited and rises to a 3d orbital. In addition to chromium and copper, there are 10 other elements that are different from the expected configuration model. They are niobium, molybdenum, ruthenium, rhodium, palladium, silver, platinum, gold, darmstadtium, and rubidium. Electron configuration always begins the same way. Sublevel 1s fills first, followed by 2s, 2p, and so forth. Because the beginning of the electron configuration is always the same, it isn't always necessary to write it. Using noble gas notation, we can avoid writing the positions of all the inner electrons. Instead, we can just write the symbol of the preceding noble gas in brackets and write the portion of the electron configuration coming after it.